Maybe you know. Science meets the questions you never thought to ask. In February 2023, an astronomer named Ivo Labbé opened a file of new images from the James Webb Space Telescope. He was looking for faint red dots, the first galaxies ever born. He found 6. Then he started calculating their masses. He stopped. He ran the numbers again. He called a colleague, because if his math was right, these 6 galaxies couldn't exist. Not this early. Not in any universe that obeys the rules we wrote. For 30 years, we thought we understood how galaxies are born. The story went like this. The Big Bang, a universe of hot soup. For 380,000 years, nothing but plasma. Then the lights went out. Cosmologists call this the Dark Ages. Hundreds of millions of years where the universe is cold, dark, and empty. Slowly, gas pulls together. Slowly, the first stars ignite. Slowly, those stars clump into the first proto-galaxies. Tiny, faint, disorganized. By the time a universe is 500 million years old, these baby galaxies are barely bigger than star clusters. That was the prediction. That was the math. The Hubble Space Telescope, in its deepest exposures, seemed to confirm it. In 1995, an astronomer named Robert Williams pointed Hubble at a tiny patch of empty sky for 10 days straight. The Hubble Deep Field, 3,000 galaxies, most of them small, faint, blue smudges from the early universe. Everything looked young because everything was young. We built a cosmology around that picture. Lambda, cold dark matter. The reigning theory of how the universe assembled itself. Then we launched a better telescope, and the picture broke. On December 25, 2021, NASA launched the James Webb Space Telescope from a jungle in French Guiana. A 6.5-meter mirror folded like origami. 18 gold-coated hexagons. A sunshield the size of a tennis court. It traveled 1 million miles from Earth to a gravitational parking spot called L2 and unfolded itself in 344 separate steps. Any one of them could have killed the mission. None of them did. By July 2022, the first images came down. Galaxies 4 times sharper than anything Hubble had ever seen. Webb sees in infrared, the wavelength that ancient light gets stretched into after billions of years traveling through expanding space. So when Webb stares at a faint red dot, it's looking back in time. Then came the deep fields, the CERS survey. Jades, hundreds of hours of exposure on patches of sky no bigger than a grain of rice held at arm's length. Astronomers expected to see what Hubble saw, only sharper. They didn't. They saw galaxies that looked too bright, too red, too organized, and way too far away. By the end of 2022, the data was undeniable. Something was wrong. To understand the crisis, you need to understand how astronomers measure a galaxy they can never visit. Every galaxy we see is moving away from us, dragged apart by the expansion of space itself. As it moves, its light stretches. Blue light becomes yellow. Yellow becomes red. Red becomes infrared. The more it stretches, the further away the galaxy is, and the further back in time we are looking. Astronomers call this number the redshift, abbreviated Z. AZ of 1 means the universe was about half its current age. AZ of 7 means we're peering 13 billion years into the past. AZ of 14, the highest Webb has confirmed so far, means we are seeing a galaxy as it was just 290 million years after the Big Bang. Now mass. The brightness of a galaxy, combined with its color, tells you how many stars it has and roughly how old they are. Heavier galaxies are brighter. Older galaxies are redder. You feed the spectrum into a model, and out pops a number, the stellar mass. For a galaxy at Z equals 10, that number should be tiny. A few 100 million suns. Maybe 1 billion. Not more. But here's where the rules break. In February 2023, Ivo Labbé and his team published a paper in the journal Nature. They had found 6 galaxies sitting between redshifts 7 and 10, when the universe was only 500 to 700 million years old. The masses they measured were not a few 100 million suns. They were 10 billion, 100 billion. In some cases, comparable to the Milky Way today, a galaxy that took 13 billion years to grow. These red dots had done it in less than 1. The cosmologist Mike Boylan-Colchin at the University of Texas ran the numbers. In a standard lambda CDM universe, The maximum mass a galaxy could possibly have at that age is set by how much matter is even available within the volume of space that has collapsed by then. You cannot have a galaxy heavier than the matter inside the bubble it formed in. Labbé's 6 galaxies broke that ceiling. Some of them appeared to contain more stars than there should have been raw material to build. It wasn't a small error. It wasn't off by 10%. It was off by a factor of 100. Either the measurement was wrong, or our cosmology was. The community split. One camp tried to kill the result. The Lab 6 were photometric candidates. Their distances estimated from broad color filters, not pinned down by precise spectroscopy. Maybe some were closer, dusty galaxies that only looked ancient. Throughout 2023, follow-up spectra came in. A few candidates moved closer, but not all of them. The high redshifts kept being confirmed. Then, in May 2024, the JADES collaboration announced a galaxy named JADES, GS, Z14-0. They had a spectrum. The redshift was 14.32. The universe was 290 million years old when this galaxy emitted the light that Webb caught. The galaxy was about 1,600 light-years across, with a stellar mass of several hundred million suns and active star formation. Officially the most distant galaxy ever confirmed, and far too luminous for its age. Then came another, JADES GS, Z14-1. Then galaxies at redshift 13.2, redshift 12.6, all overproducing light. A team led by Hakim Atek at the Institut d'Astrophysique de Paris counted. Webb was finding roughly 4 times more bright early galaxies than the standard model predicted. That isn't statistical noise. That is the model telling you it has a hole in it. And nobody could agree on what was leaking through. And just when it looked like we'd have to rewrite cosmology itself, a new possibility emerged. One that was almost stranger. Maybe the galaxies aren't massive at all. Maybe they're hosting monsters at their cores. In 2024, a Yale astronomer named Ivo Labbé revisited the Lab 6. Using updated models, he showed that if you assumed the bright central light came not from billions of stars, but from a single supermassive black hole devouring gas, the stellar masses dropped by a factor of 10. Suddenly the galaxies fit lambda CDM. But this fix has its own problem. To produce that kind of light, you need a black hole already weighing tens of millions of suns, just 300 million years after the Big Bang. That black hole had to grow somehow. From what? A second theory came from Joseph Silk at Oxford. He proposed that early black holes and stars formed together in a feedback loop, a symbiosis that explained the over-bright galaxies without breaking physics. A third theory suggested early stars formed faster and more efficiently than any star formation we see in the modern universe. 3 theories. 0 agreement. The universe is keeping its secret. This isn't an obscure argument between professors. The lambda CDM model is the foundation of almost everything we believe about cosmic history. Dark matter forms the scaffolding. Gas falls into the scaffolding. Galaxies grow. Solar systems form. Planets cool. Life appears. The model predicts the temperature of the cosmic microwave background to 10 decimal places. It explains the large-scale arrangement of galaxies, the abundance of helium, the ratio of hydrogen to deuterium. It has been right about almost everything. And yet here we are, 3 years into Webb's mission, watching it struggle to explain the simplest thing, how soon something can be big. If the model is broken, we don't know what replaces it. Modified gravity? A different kind of dark matter, warm instead of cold? A first generation of stars so massive they would outshine entire galaxies? Every possibility leads somewhere uncomfortable. Right now, in observatories from the Atacama Desert to Mauna Kea, follow-up programs are racing to catch more spectra of these distant red dots. Every confirmation is a brick pulled out of the foundation. And the foundation, so far, is holding barely. Webb is still scheduled to operate for at least another decade. We're not done being surprised. Back in Melbourne, Ivo Labbé and his team keep counting. Every new release of JWST data, every new spectrum from JADES, every new survey, more red dots, more impossibilities, more numbers that should not be there. He has stopped saying the galaxies break cosmology. He says, carefully, that they tension the model. But tension is what makes things crack. The James Webb crisis is only 3 years old. We don't know yet whether someone will look back at the Lab 6 and shrug, the way we shrug at correlations that turn out to be noise, or whether some graduate student, watching the data come in tonight, is sitting at her desk doing exactly what he did, running the math, running it again, calling a colleague, because in front of her on her screen is something that by every law we wrote cannot exist. Next time on Maybe You Known, what if the universe isn't expanding evenly? In 2023, a team in Hawaii measured the speed of cosmic expansion on opposite sides of the sky and found 2 different answers. The universe might not be uniform. It might have a preferred direction. We'll show you what they saw and why it could be the second cosmological crisis no one is talking about. Thanks for watching. If this sparked a question, drop in the comments. It might be our next video. We'll see you next time.